Hello everyone, now I'm going to demonstrate how to model this problem in ABQUS. So we are going to perform a buckling analysis using static riks, because in buckling analysis we usually have softening behavior, and buckling analysis will be a good illustration of use of static riks in ABQUS. So the question asks us to use shell elements. So first is shell elements, and the load displacement curve of a metal given in assignment 7. So the material input is elastoplastic, and find the relationship between the applied moment and the end rotation. So we are going to apply a moment here, and thus we will have a rotation. We are going to find the relationship between the moment and the rotation. And the PEP segment has a length of 4.5 meter. And the outer diameter is 0.9. So OD is equal to 900 millimeter, and the thickness of the pipe is 9 meter. So compare the elastoplastic buckling behavior of the pipe with and without internal pressure. So we are going to simulate this pipe twice. First with internal pressure, and another case without internal pressure, and this is the pressure that we need to apply to the pipe. So it's equal to P is equal to 0.8 times the 2 times the thickness, which is 9 millimeter, divided by the diameter of the pipe. It's 900 millimeter, times the yield price of the material from assignment 7, which is 800. So this will give us a value of 12.8. So here are some hints. Use symmetry. Since this pipe is a plane symmetry structure, so we can only model a quarter of it. And for the case of internal pressure, apply the internal pressure in an initial step before applying the moment, because the moment is applied later. So we need to apply the internal pressure before the step of applying moment. Otherwise, if you apply these two loads in the same step, so you will use the static riks method for both loads. So we are only interested in using static riks method for the moment, and apply the end moment on a rigid end. So we are going to apply the moment to this rigid end here. Now let's create a part for this structure. So remember, we are going to model a cut of it, and since the pipe is a thin wall structure, so this time we are going to use a 3D model space deformable and shell for the shape, and we are going to extrude the sketch to get this shape. Since the diameter of the pipe is 900, so here we can just put 2000 and hit continue. So we are going to create the cross section of this pipe. So the first point is 0, 0. And here I'm going to show you another way to create an accurate geometry. So we can pick a syndrome point, and we can use add dimension to make this geometry accurate. So here we can input 450 because the diameter is 900. So we hit enter. Now this circle has a radius of 450. So since we are going to model a quarter of it, so we need to delete, we just need a half a circle. So we can use, we created a line so that we can trim this part. So we are going to use auto trim. Then we can trim this part. And then you can use auto trim to delete this part, or you can use this option to delete this part. So as you can see here, we have a geometry that is not closed, because we are going to create a shell shape with a thin wall structure. However, if you recall what we used for solid shape, we always have a closed shape, closed sketch. Now click down and click down. Here we need to input the length for this path. So we are going to model a quarter of it. So the length is half of this. So it's 2,250. 2,250. Click OK. So you can see now we have this beautiful path. It's a quarter of the path. And next part. So since we are going to perform a Barcode analysis, so we need to introduce some imperfection, because in ABQUS, the geometry is perfect. It's we don't have any cavity inside, and the material model is perfect. However, in reality, we always have some imperfections, like slight changes of dimensions, or some flaws inside the material. So here, in order to perform barcoding analysis, we need to introduce some imperfections manually. So here I'm going to I'm going to divide this part into two components, so that we can assign different sections for these two components. So here we need to, in order to do that, we need to create a datum plane. So let's click create a datum plane. Since the sketch is created in XY plane, so we can just create a datum plane that is with the reference of XY plane. So we click XY plane. And here we can just put the offset, so we can put like 200. So because we want a larger thin surface, so that we can simulate barcoding analysis obviously. So let's hit enter. And then we have created this datum plane. Now we need to divide this surface into two components. So here we use this create a partition function. So we need to put the tab to face and use datum plane. And now we select this datum plane and click create partition. And now you can see we have two components. And then we can assign different cross sections to this two components. Or we can just assign different materials to these two components. Now let's go to the material property. So we are going to create a elastoplastic material. So let's go to first create elasticity. So it's 200,000. And the percent ratio is 0.3. And next we are going to define plasticity. So for convenience for the demonstration here, I'm going to use the two data points. So the yield stress is 800, and the plastic strain is 0. This is the first point. For the next point, I'm going to use once the last data point we got from the material curve. So it's this. So, but for your assignment, you need to use the entire material. You need to use all plastic, all yield points instead of using 2. Okay, this is just for the demonstration. Now let's click OK. Now we are going to create 2 sections. The first one is called a normal section. For normal section, we are going to use the shell homogeneous, and the thickness is 9 millimeter. So we can see the thickness is 9 millimeter. And for the material, we are going to use material 1 and click OK. Now we still need another section for this part. So let's call it thin section. So it's a shell homogeneous, and for this one we put 8.5. So we use a thinner, shell thickness. Click OK. And now we are going to assign section 1 to this component. So here, when you use shell section, you always need to define the shell offset. So here you can see we have this reference surface. This is the surface that we just created. However, when you assign the shell elements, it has a thickness. So you need to decide which surface you are going to align with this reference surface. So here, if you put a middle surface, so this middle surface is going to align with this reference surface. So if you put a top surface, so this surface is going to align with this reference surface. Similarly, if you put a bottom, this surface will be aligned with this reference surface. So for our situation, you can see 0.9 meter is the outer diameter. So our shell thickness should within this reference surface. So since here we need to use the bottom surface, let's click OK. And similarly for this one, we are going to assign this thin section to this surface. And we are going to put a bottom and click OK. So here, we can also visualize the thickness of the shell by click View and part displacement display options and click Render Shell thickness and click Apply. So you can see we have some imperfections here, right? Yeah. And you can see the reference surface is here. It's the outer surface. Let's click, let's just untick this. Okay. Now we have material properties. Next, we are going to mesh this part. So we are going to use global size. So let's put 20 and click Apply. Click OK. Now we can just mesh it. Click Yes. So you can see we have a less mesh, right? Now we can just assign the material, assign the element types. So as I said earlier, here we can use the 2 different element types because we have 2 components. So for example, so we can just select this half and then we can assign 1 element type. And once we're done, we can just we can assign the other half. However, for this demonstration, I'm going to use the same element for this pipeline. So I'm going to use the for integration, and you can see here it's a shell elements with 4 nodes. Click OK. Now we are going to create an instance. Let's click this and click OK. So you can see we have 1 instance. And next part, we need to create a step. So for this app, we first need to apply pressure. So let's create a step called pressure. So pressure. And this step, because we are going to apply pressure, so we are going to use a static general. And so you can see we are going to apply a pressure which is equal to 12.8. And if you apply this pressure to this PEP, so the pressure will be applied to the inside surface like this, and the circumference stress will be equal to this value, which is 800. So our yield stress is 800. So here, when you apply the internal pressure, so it's a linear analysis. So you can use the on, or you can use it. You can turn off the nonlinear geometry. So here you can put it as 1 and click OK. So here we have 2 steps. So I'm going to apply boundary conditions first. So you can apply boundary conditions, symmetric boundary conditions in the first, in the initial step, or you can just apply in the pressure step. It doesn't matter. So I'm going to apply boundary conditions, symmetric boundary conditions in the initial step. So for the initial step, we have 2 symmetrical boundary conditions. For these 2 edges, we are going to apply X symmetry. So you click continue and select regions for boundary conditions. So we select, we hold shift, select this edge, and this edge, and this edge, and this edge. Then we click done. And for these 4 edges, we are going to apply X symmetry. And now we create another symmetry boundary condition, which is Z symmetry. Click continue. And we are going to hold shift and select this edge and this edge and click done. So this is Z symmetry. Click OK. So now we have applied the boundary conditions. So for the pressure step, we are going to apply internal pressure. So let's create a load first. So it's called let's call it a pressure load. And we are going to apply pressure, continue, and we are going to hold shift, select these 2 inner surface, and click done. So you can see we need to specify which surface we are going to apply pressure, because this we have an inner surface and outer surface. So we are going to apply internal pressure. So we need to use we need to select the internal surface. So it's brown, and the value is equal to 12.8. Click OK. So you can see the pressure is applied internally. So for the next step, we are going to apply a moment at this end. So in order to do that, we need to create a rigid body. So we go to the interaction, and in order to create a rigid body, we need to tell the software which reference point the rigid body will attach to. So we need to first create a reference point. Let's select this point as our reference point, and then we go to create a constraint to create a rigid body constraint, and click continue. So we are going to select this edge. So the rigid body constraint means all the degrees of freedom of this edge will be attached to this reference point. So all degrees of freedom of this edge will be exactly same as this reference point. So we are going to use type, and we are going to select this edge, hold shift, select this edge, and now we click down, and then we need to select the reference point, this point, and then we need to click OK. And now we have created a rigid end, and this rigid end is attached to this reference point. So for the pressure step, so I'm going to fix this point to test if pressure is successfully applied. So let's create another boundary condition called a fixed pressure, fixed moment point. So let's select this point and click down and use the encapture. Okay, now we have everything for pressure step. Now let's check this model first. So we are going to create a job called check pressure, and click continue, and click OK. Now we submit this job. So we can open moment to check the status of this job. So we can see here the job has completed successfully. Now it's completed successfully, sorry. The previous step called analysis input file process completed. So you can see this is a linear analysis, right? We only have one increment. Now let's check, let's turn off this and check results pressure. So you can see here the emissive stress is 600, so which is not 800 as we expected. So this is because what we see here is the stress at bottom nodes. So this is the shell cyclis, right? And we have integration points across the cyclis direction of the shell elements. So the default result is the stress at this point. So let's go to the results and history output. Sorry, it's called results field output. So we need to select the section points. And here, so the default one is the bottom. So if you put it to top, so it will show you the stress at the top load. So for shell elements, we usually use the envelope. So it gives you the maximum stress point, stress across the entire cyclis direction. So let's put it to envelope and click OK. Okay. So you can see now we have a circumferential stress at this thin cross section, which is equal to almost 800. Now it means our pressure is applied successfully and it's correct. Now let's create another step, which is called, we are going to use the static riks to perform barcoding analysis. So let's go to step and create another step. This step we call it, for this step we call it barcoding analysis. And we are going to use static riks. Click continue. So here you can see we need to we can put stopping criteria. So we can use a maximum load proportionality factor or we can give maximum displacement at which degree of freedom, or you can just leave it as it is, and we can terminate the job manually when necessary. So here, because it's a nonlinear analysis, so I'm going to start with a small initial arc length increment. So I'm going to now click OK. So for this step, we are going to apply a moment load here so that we can perform a buckling analysis. So, but in the previous step, in the pressure step, we constrained this point. So any boundary conditions you applied in the previous step will be carried out to the next step. For example, here we applied X and Z boundary condition, and for the next step, these two boundary conditions will be carried out to the next step. We don't need to apply these two boundary conditions again. Similarly, if we applied a fixed moment point in the second step, so in the third step, it will be carried out. So here we need to deactivate this first. And then we are going to apply a moment to this reference load. Let's call it moment, and click continue. Select this reference point and click down. So let's put a larger value, which is 1 times 1 times 10 to the power of x, and click OK. And then we also need to constrain this point. So let's constrain this reference load so that we can make sure that the pipeline will buckle. So let's select, let's use the displacement and click continue, and select this point and click down. So we are going to constrain all degrees of freedom except rotation along x direction, and click OK. So now we have everything. Let's create another job. So it's called buckling analysis. So click continue and click OK. Now let's submit the job. So let's open the monitor to see the status of our job. So we can see here the analysis input file processor completed successfully. And now step 1 has been successfully simulated, because the step 1 is a pressure step and it's linear. Now we are in step 2, which is buckling analysis. So we can also check the results during the simulation. And this will take a while, so I'm going to pause the video, and when the job is done, we can come back to take a look together. After the simulation, you would see that your structure would look like this. It would either buckle here or here. This is the plane of symmetry. So there is one thing that I want to mention, is that with the previous sighting, we introduced imperfection here. So previous sighting, I put 200 for the offside of this datum plane. However, when I use that sighting, the softening behavior of buckling analysis wasn't obvious, so I put it to 20. And then after you made this modification, you need to mesh your part again using seeds and mesh again and assign elements type again. And then you can submit your job. And after simulation, you will see that your part is going to buckle like this. And you can check the result frame by frame. So let's put the stress as well. You can see this is a pressure step. And the pressure step, for pressure step, we only have one. Is the increment is 1, you can see here. And the next step is a nonlinear buckling analysis. So we can see that the part is buckling. You can see all the way here. Yeah. So after simulation with the internal pressure inside, you can see that the pipe buckle outside. If you reduce the pressure to 0, you will see that this pipe will buckle inside. So now let's check the results. So the question asks us to compare, the question asks us to find the relationship between the applied moment and under rotation. Now let's check that. So we can check the load proportionality factor from here. Load proportionality factor. So you can see that our accumulated load proportionality factor increase first, and then here decrease a little bit and increase again, and then decrease a lot, almost to 0. So let's save this. So let's call it LPF and click OK. Now we need to export the rotation at this reference point. So we go to Tools and XY Data, Grid, and we go to ODB file output. And here we use a unique loader. And we are interested in the rotation around the x-axis, right? So let's select UR1. And now we need to select this point. So let's select this point and edit selection. Now we have 1 point selected. So if you plot them, you can see mixing steps with time and arc length domains. So that's because you can only export results for one step at a time. Now let's untick pressure step. So we can just have a buckling analysis step. Now click OK. This time if you click plot, you can see this is the relationship between the angle and arc length. So it's increased all the time. So now let's save this as well. So click OK. So now this data has been saved. Now let's export this to a txt file, LPF and this. So this two is exactly the same, so we just need one of them. Let's call it LPF and angle .txt. Let's click OK. So we can find this file here, right? Now let's open Excel and check the results. So file, browse. Let's go to all files and go to the default folder C and temp. Click this file. Click open, and we are going to use the fixed device to divide this the data into 3 columns. So next, finish. So here we have this is arc length. So this is LPF, and this is the angle. So let's put an angle here, and we need to find the relationship between the rotation and the applied moment here. So the angle is equal to this, right? And the angle is in radius. And the moment is equal to load proportionality factor times the extra load that we applied, which is 1 times 10 to the 8th. So this is our applied moment. Now let's drag this all the way to the last data set. So let's plot this. Insert plot. You can see here we can capture this moment and rotation curve. So you can see after this point we have some softening effect here. So this is a moment, right? So now let's put the label. So this is a moment. This is the angle. Now we can see clearly as the angle increases, the moment first increase, and then here we have some softening effect, and then we have a more softening effect. And using static riks method can track this response well.